Transformers. Structure matters, order matters. For example, a time series is a time-ordered sequence of numerical values, and a sentence is a structured sequence of words. A 2017 paper, Attention is All You Need, introduced a deep learning layer called a transformer that is impressive for its ability to learn structure. So here is a transformer. Inputs next to outputs at the same level. Positional encoding models structure. A multi-head attention is a model of query plus key implies value, much like what we do when we Google. Each is a neural network. The outputs can either be learned or generated. In other words, this is a generative model. But it needs a huge amount of data. So let's look at this a little more closely. Here is the transformer architecture. And you'll notice that it's got two parts. It has an encoder, a BERT encoder, a bidirectional encoder representations from transformers, and it has a GPT decoder, generative pre-trained transformer, as we can see over here. So notice the encoder and the decoder are next to each other. So let's explain how that works, how you can actually have an encoding and a decoding when they're parallel rather than one leading to the other. In other words, let's look at the details. So to begin with, suppose we have some large collection of documents, that those documents are all sentences. So over this huge number of sentences, we have the set of all the words in all of those sentences. And notice that I have some example here of 1,000 words, so to speak, starting with A, ending with 0. And I've labeled these with V1, V2, V3 up to V1000 respectively. So for example, if I've got a zoo with 0 zebras and apes adds an ape, well, the first thing I actually do is called lemmatization. I take all the words back to their root forms. And then I assign one of these V values to each word corresponding to where it occurs in this list. Notice that ape occurs twice, and we have the V4 twice in this sequence of V's. Our input is then this sequence of V's corresponding to whatever sentence we're looking at, and our output has a mask where one of our values is. In this case, we're masking off the word 0. So we present the input to the input embedding and the output to the output embedding. And then at the top, we get probabilities. And it predicts the probability for each word being the word that should replace the mask. So in the training step, we simply put a 1 corresponding to the word 0, which is our last word in this case, that should replace the mask. And so this transformer learns to replace missing words with words that best correspond to what it's learned from this huge collection of documents. Once we've done all that, we can simply use the GPT structure and give it masked values in the output, and it will predict probabilities for the words that have been masked out. So for example, ChatGPT, you ask it a question, and the set of words is then the response is masked off, and it predicts what words come after your question corresponding to the highest probabilities. So let's look more detail what these V's are actually giving us. They're actually what are known as word embeddings. They're vectors in a vector space, and what we do is we take each word and associate it with a vector. For example, using word2vec. We could either learn these or we could pre-train and use the vectors that we've pre-trained for these. Very often, though, we just simply learn them. For example, here's a poem by Joyce Kilmer, a very famous poem. And let's notice that I can tokenize that into a bunch of sentences. In this case, each line is considered a sentence, and then I can start learning word embeddings. So here I'm showing you the Python for importing a word to VEC, and we get a vocabulary of 65 words. For example, tree is represented by, I'm going to show you an example in 2 dimensions. Usually our vector size would be, say, 100, but I wanted to show you a simple illustration, so I'm using a very small vector size of 2. So this is a vector in the XY plane. And here are what is learned to be similar to tree. Arms, the as, made, shall, lovely, can, to, mouth, robins. So let's give it a phrase. A poem as lovely as a tree. So when we do our embedding, then we actually end up with this set of 2-dimensional vectors. Each row is a vector. And so now we have a set of points in the plane. That is, these are points in the plane. But notice that the V0 and V5 are the same. They're both the word A. And the V2 and the V4, they're the same. They're both the word as. So we have these points that are word embeddings, and we have unique vectors for each word, but we've lost the information about where these words are in the sentence. Now we want to think of these as actually being vectors, but we don't have any positional information. In other words, the word order of the sentence is not represented by these vectors. So what we do is called positional encoding. And here we have a encoding of the positions in the sequence. So notice that P0 corresponds to the first word, P1 to the second, P2, and so on. And each of these are distinct positions. So what we can do, and this is actually, we're using what's called a Fourier basis, and what we can do is we can add the word embeddings to the positional encodings, and we get a set of points that are somewhat like perturbations of our actual positional encodings. And what we have is we've retained the information from the word embeddings, but we have a distinct position for each word. So in other words, we've encoded both the word embeddings and the sequence structure of the sentence. So a softmax is where we have e to the xi over the sum sub j's of e to the xi. And this is what's known as a Gibbs form. And there's one of these exabytes for each of the 1,000 words. And we have these attention heads. An attention head is this structure that's inside of both of these. Actually, they're multi-attention heads. We'll see that in a minute. And our input, as we've already seen, is these vectors, these word embeddings, and then we do the positional encoding. That gives us some x. And from there, we go to the q, the k, and the v. These are matrices, linear transformations. So we actually end up with a qx, a kx, and a vx. Then we do a matrix multiplication of this form. And notice we have x at the beginning and x at the end. So that means we're looking at the word position combinations with respect to themselves. And we take a softmax when we do that, and that softmax is going to give us numbers between 0 and 1. And we're going to think of these as edge weights, or multi-weights if you want to think of it that way. Now what I mean by that is here was our positional encoding, and we want to think initially that we have an edge between every one of these points. But then when we get our A, we actually end up with the softmax giving us some of these edges have weights very close to 0 and some have weights close to 1. And what that does is the zero, close to zero weights, prunes away and leaves those edges that give us the important relationships among words in our sentences. So we have a structure for our sentence, not a sequential structure, but a relevance structure, which words are related to each other in the sentence throughout the entire sentence. Then we do a matrix multiplication times a Vx, but notice this A is only going to use this structure when it modifies the Vx. Now we actually have multi-head attentions. This is sort of similar to when we did convolution. We had multiple kernels coming out of each convolution layer, and here we have multiple of these attentions coming out of each multi-head attention. Now, here's a question which has probably occurred to you and certainly occurs very frequently. How do you know which activation to use? One of the things you may have noticed was there was no ReLU in this transformer model. So when do you use a ReLU versus when you use a sigmoid? Well, there's a real advantage to using ReLU activation because you get convex optimization. And your universal approximation corresponds to polygonal spline approximation. You're doing piecewise linear approximations of the functions. And of course, you can get a universal approximation of a function if you just do a fine enough piecewise linear approximation. Sigmoid activations are not convex, so we lose the convexity when we start using these sigmoids. So remember, our sigmoid looks like this. It's the logistic function, and it's between 0 and 1. And notice the derivative is equal to sigma times 1 minus sigma. Now that means if I take the derivative of the log of sigma, which I very often do, because if you remember our cross entropy, binary cross entropy, very often our loss functions are in terms of these logarithms. And then when I take a derivative, I get the derivative over the function itself. But notice that's sigma times 1 minus sigma over sigma, and that's just 1 minus sigma. Now what does that mean? Well, that means if I take the derivative of sigma of a kernel, then I end up with 1 minus sigma of the kernel times the derivative of the kernel. Now this derivative of the logarithm equals 1 minus the kernel. The sigma is between 0 and 1, so this first part cannot be equal to 0. So that means to get 0, we have to look at the kernel. And what is the kernel when you have an architecture? Well, if your last layer is this fully connected with a sigmoid, a sigma activation, then everything leading up to that architecture that determines the feature engineering and the feature representations you're learning, that's your kernel. And notice that using a sigmoid activation means that with your cross entropy or KL divergence or whatever loss, that you're actually modifying the architecture deliberately to give you the features you need to make your predictions. So given that, let's take a top-down view of our transformer. Notice we have a final softmax layer. That is a sigmoid activation, which means this entire transformer structure is really an architecture. It's a realistic implementation of a kernel type of structure, a feature engineering design. Now in the tension head, the softmax was used, but it wasn't used in the same way. It was here used to map edge weights from 0 to 1. The outputs are presented to the output layer via a mask that blocks word positions we desire to predict. And then that final softmax activation predicts the missing word, the one with the highest probability, is the one that should be placed in the masked position. So the architecture of a transformer is actually submodels glued together by these add and norm layers. Norm here is just built-in pre-processing. It's standard scaling before we go to the next layer. However, the vanishing gradient is still a problem. So add is a residual step. It keeps the gradients from vanishing as you backpropagate over huge numbers of layers. And to do that, this actually was discovered by Microsoft in their ResNet models. If X is the inputs and F sub L is the Lth layer, then what you do is you take the X forward and add it to the output F sub L of everything that came before. And you can see that here, these arcs upward to the added norm parts. So we take word embeddings plus positional encodings and we send that through our multi-head attention layers. But notice that each one of these attention layers, and there's H of them, and Q, K, and V, those tend to be fairly large matrices. So what do you end up with? Huge numbers of parameters. That's why you have to use a massive amount of data to train a transformer. There are so many parameters that have to be trained. But the transformers learn structure. They do it very well. In fact, they're a special type of what's known as a graph neural network. Graph neural networks model structure by networks. So we started with a complete graph, and then we learned how to prune away the edges we didn't need. In other words, we learned the relationships between words in a sentence or between points in a time series, the relationships that are important to making our predictions. And we do that by essentially eliminating irrelevant edges and working only with the relevant edges and therefore the learned structure. Then we can use that structure, those relationships, to make predictions, including predictions of structure itself. And that means that the transformers are a generative model, but they don't just generate new data, they also generate new structure.